We have recent papers about generalized Hall current and gapless defect fermions, please.
Thanks everyone for coming to my talk, and I would like to thank the organizers for inviting me to give a talk here. So some of you have already heard this talk one time. I hope that it's a little more clarifying this time. I have to warn you, I will spend quite a few slides trying to clarify what the goal of the work that I'm presenting is and what it is not. So I have quite a few slides on this. Hopefully that's not exhausting. So I'm going to talk about a certain idea of generalizing the picture of Hall current for general gapless fermions that live on defects. This work that I'm presenting today, you can find them on arXiv, the arXiv numbers. This was done in collaboration with David Kaplan at the University of Washington. Okay, so let me unpack the title a little bit. So in this talk, I'm just going to address gapless edge states in free fermion gap theories. So these are all going to be some relativistic QFT, which describe topological materials. And I will share with you a framework that unifies all of these edge states in a single picture that resembles the Hall effect. And I will demonstrate how this works in one particular example. And again, since I'm just addressing free fermion theories, I should mention that here, for free fermion theories, this entire picture actually relies on calculating one-loop Feynman diagrams. I will hopefully find time to elaborate on the role of topology of free Dirac fermions in this picture. And eventually the goal, which I will not get to in this talk, is to take this framework and extend it to interacting theories to distinguish between gappable and gapped phases, or gappable and gapped fermions that live on defect. So why am I doing this? Here is some context. So I am a quantum field theorist trained to deal with problems in QCD and effective field theories. It's only recently that I have started working on this topic of topological insulators and quantum Hall effect. So how did I get into this? Well, so here I will give you some historical context. So it turns out that the physics of quantum Hall effect has deep ties with how QCD is simulated on the lattice. So in earliest days of QCD simulations, people faced a certain challenge known as the fermion doubling challenge, which is that if you took a fermion, let's say in a four-dimensional theory, and you naively discretized it, you would end up with extra flavors of fermions, which you didn't want in your theory. And there was, at the time, there was no way of getting around this problem. This is also related to the Nielsen-Ninomiya theorem, which is stated here. And so people came up with several quick fixes to solve this problem. So the problem you can see already here. So you take the naive fermion, and if you discretize it, its dispersion relation looks something like this. So in general, if you are not on the lattice, you would get a p square minus n squared equals 0. And if you set m to 0, the fermion mass to 0, you get p equals 0 as the pole of your propagator. But on the lattice, the p gets replaced by a sign. So you get two poles, one at p equals 0, another at p equals pi. Now, if you set m to 0, the mass to 0, you get some chiral symmetry, but you get this doublers, fermion doubling. This is the fermion doubling problem. So there is a quick fix to this, which involves shifting the fermion mass by what is known as a Wilson term. So this is basically R, some Wilson parameter, times a gradient square. Okay? And so the corresponding dispersion relation looks like this. And so that would be the pole of your fermion propagator. And as you can see, at this point, now p equals 0 satisfies this equation, but p equals pi does not satisfy this equation anymore. So you have gotten rid of the doublers. So these are called Wilson fermions. But the problem here is that you still have radiative corrections which destroy chiral symmetry. So it's not an ideal way to simulate QCD if you really care about chiral symmetry. So if you set this mass term to 0, for example, p equals 0 is the only pole that you have, but you get corrections to the fermion mass that are at the cutoff scale because of this term. Okay. So here's a better fix, which relies on the idea of, or rather, the idea of domain wall fermions, which has deep connections with quantum Hall effect. So the idea is similar. You now look at, let's say if you have a 4-dimensional theory, you extend it to a 5th dimension. So you have a 5-dimensional quantum Hall sample, and your 4-dimensional world that you want to simulate is at the boundary of this quantum Hall sample. And if you are able to separate right chirality fermions from left chirality fermions, then radiative corrections are not a problem because you have physically separated the two modes, and the radiative corrections are exponentially suppressed, right? Because the fermions have, the wave function of the fermions overlap minimally in this case. So this is something my collaborator did in 1992. He proposed this and it seemed to work really well. So this is the idea of domain wall fermions is just a relativistic quantum Hall effect in 5 dimensions. So this is very useful for QCD simulations. However, so what you do in QCD is that you take the left-handed fermion here, the right-handed fermion here, and together you say, okay, they describe a 4-dimensional world of Dirac fermions. So that's how QCD is simulated.
Have people used it in simulations actually?
Yeah.
Because you pay cost for the extra.
Yeah, you do, but there are some problems where you are willing to pay the cost because you really care about chiral symmetry. So if you are interested in chiral phase transition, for example, as a function of temperature, so that would be where you would really want a good chiral symmetry in the long run. But the same thing, having
the extra dimension in simulation doesn't have to be large. How large does it have to be?
It has to be large enough for this wave function to fall off. So it will depend on what your domain wall height is.
Mm-hmm.
And
isn't that the mass that you put in by hand?
Mm-hmm.
You could crank that up to a lattice scale.
Yeah, you can make it. You can almost make it as good as you want. But then once you turn on the gauge field, and if you go to strong coupling, then that can mess up with how well the fermions fall off. Mm-hmm. And so there are some constraints coming from there. But in general, it works very well. Yeah.
So you build the domain wall by hand in this simulation?
Yes.
My understanding is, is it like is it a loop that you make? You make a loop.
Yeah, yeah. You could also make a slab, but this is a loop. So you identify this point with that endpoint. So you get a wall and an anti-wall.
And the mass jumps or something.
Yes, like that.
Yeah.
That profile. So you are always in a finite volume when you're simulating, and that's good for QCD simulations because one wall is left chirality, other wall is right chirality, and together they make a Dirac fermion. But this very thing that you're in a finite volume is a problem if you want to simulate chiral gauge theories. Because if you start with a vector-like theory and put this theory with fermions on a finite volume, you will always have this left and right chirality fermions, and your gauge field end up talking to both of them. And so you end up with a vector-like theory, and it's very hard for people to make the gauge field only talk to one of the fermions, one wall and not the other. So that sort of has been a challenge for chiral gauge theories.
But cannot you just perform measurements near one wall?
I think that's difficult because both walls are massless, so they get the results get corrupted. I think if you just try to do that, because the gauge field ends up living both here and here. So, yeah. In principle, you could try to, kill off the gauge field here, but it hasn't worked so far in a convincing way. Okay. So, what people have been trying to do for a while is, take this wall-anti-wall system and gap out the massless fermions or the chiral fermions living on one of the walls and while leaving the other one untouched. If you are able to do that, so for example, if you have multiple flavors of fermions, you might be able to gap out one wall by putting in some interactions on that wall itself. And then at low energy, the hope is that you'll be left with a chiral gauge theory. Yeah. And so there have been several proposals exploring this idea, and they're all inspired by, recent, at least the recent work on this idea has been inspired by this paper by Fitkowski and Kitev for 1+1D Majorana chains, where you have again a wall and let's say if you have a wall and an anti-wall, you will have Majorana edge states living on the two walls, and you can gap them out on one wall by just turning on some quartic interaction. And there are several papers exploring this idea in different ways. Now, I am not going to actually suggest any solution to this problem. That's not what I'm trying to do here. What I want to mention is that if you really want to use this idea of symmetric mass generation, so in the case of chiral gauge theories, you would want to preserve chiral symmetry while trying to gap the fermions. If you really want to use that idea, it's important to distinguish between gappable fermions and gapped fermions. Okay. So this is something that is very important to do when you're trying to do the simulation on the lattice. If you are in a regime where you just have gapless fermions, then it's not going to work. And so this can serve as a motivation for what I'm discussing today.
So, sorry, maybe I don't understand. It's important to distinguish between gappable fermions and I guess ungappable.
No. So what I really mean here is that if you were just interested in anomalies, right? That may not necessarily tell you between whether your fermions are gapped or not gapped. So, for example, in the Fitkowski-Kitev case, right, you have 8 fermions. You can gap them if you turn on interactions, right? And so in that case, the anomaly is just Z8, right? So it counts gapless, 8 gapless fermions, same as 8 gapped fermions. So I'm just trying to say that anomaly wouldn't tell you what I want to do here.
But
whether
it
that was
tells-
achieved.
Is it?
But it tells you that you can gap.
That's enough. That's not enough.
Yeah, but yeah,
For the
it's the
purpose.
distinction you're making that we can be gapped.
Yes.
But if interactions are weak enough, they may remain gapless.
Exactly,
So
that's-
it's like which phase we.
But that's a question of dynamics.
Yes.
Yes. And so that's something we're hoping to capture with the tool that I'm going to describe.
I mean, I would think that's a question of RG flow, whether something is relevant or irrelevant around certain fixed points.
It depends. I mean, yes, and you have to. So when you are putting this on the lattice, you would want to be able to measure, right? Whether you were able to really gap it or not if you tune the interactions correctly. So this is a reasonable tool, we think, eventually when we extend it to interacting theories. Okay, so here are some cartoon slides explaining to the audience, those who are not familiar with what I'm talking about. So this is, I'm basically trying to draw gapped fermion topological phases with boundaries. So this one is the quantum Hall phase, 2 plus 1D bulk with 1 plus 1D edge states. So I have right moving and left moving fermions living on the edges. And you have current flowing from the bulk to the boundary when you turn on an electric field. And the chiral fermions living on the boundary carry this current. This is a 3 plus 1D topological insulator with 2 plus 1D massless edge states. This is a 3 plus 1D bulk with 1 plus 1D vortex string. Again, you can have chiral fermions here living. And similarly, this is a 2 plus 1D bulk with 0 plus 1D vortex defect. And we say that this one is special, and you will see why. So here's a slide on why we think it's special. It's because we like the picture of quantum Hall effect. So what I'm drawing here is the spectrum of a right-moving fermion living in 1 plus 1 dimension. So it's a spectrum of that fermion. So if I apply an electric field, the population of the right-moving fermion goes up. I don't have a left-moving branch, so as you can see, neither the vector nor the axial current is conserved. So this theory by itself is sick, but it can exist on the boundary of a quantum Hall sample because there is this current flowing from the bulk to the boundary, which can compensate for this current non-conservation on the boundary. Another way of saying is that you have a perturbative ABJ anomaly on the boundary, which gets compensated by gauge non-invariance of the fermion path integral in the bulk. And it turns out, of course, there's no such current inflow in other examples that I discussed. So if you have an odd spacetime dimensional defect fermion, there's no notion of chirality on the defect, no non-conservation of current, and no current inflow from bulk. There are some examples here. For example, the 2 plus 1D surface states of 3 plus 1D topological insulator, or the 0 plus 1D defect states of 1 plus 1D topological insulators. Similarly, if you don't have a continuous symmetry in your original theory, you would have no conserved current. So for example, fermion number symmetry can be broken down to Z2 by a pairing phenomena. So this quantum Hall picture, of course, does not exist for all kinds of topological insulators. However, as I was discussing with Tin, there is a bulk boundary correspondence in all of these examples that you can find if you were paying attention to global anomalies, where the existence of massless edge states is ensured by the global anomalies connecting bulk physics with the boundary through fermion path integrals. Again, it's a great tool, but may not be useful in distinguishing gappable fermions from gapped fermions. So because from the perspective of global anomalies, these two are the same. So it has a corresponding topological invariant. But in several interacting and non-interacting theories, these two are not the same things. And so you would want a different topological invariant if you want to distinguish between the two cases. So here's a summary of why I'm doing what I'm going to do. First of all, we think it's intuitive to create a Hall current-like picture. So we like it, that's why we're doing it. It's an alternative picture connecting boundary to bulk. And finally, the application that we have in mind is looking ahead, hoping to distinguish between gapable and gapped fermions for chiral gauge theory applications. So here are some features of the construction that I'm going to show you. So again, for free theories, the construction is going to be perturbative. Doesn't matter if you're describing quantum Hall effect or not. For all the examples that I'm going to discuss, it's going to be perturbative. This is going to involve the index of the fermion operator. And I will need to turn on background fields. They don't have to be gauge fields, as you will see. It's going to hold for arbitrarily weak background fields. And space-time can be open manifold. Okay, so these are some of the things that you will see as I go on. So here's the main idea on which the construction is based on. So if you have a Euclidean fermion operator, let's say with a point-like defect zero mode, so here I'm drawing both space and time, and I'm drawing the zero mode of a particular Euclidean operator that is localized in space-time, okay? In that case, there is a current, J, I call it J, away from the point defect, and we call it the generalized Hall current that flows to the defect such that the space-time integral of its divergence is 1, okay? So this is true every time you have a Euclidean fermion operator which has a zero mode localized in space-time. Yeah.
Sorry, can I ask, did you put is the Hamiltonian of the bulk theory modified? The defect is there, or?
I will come what the connection is.
Okay.
This is sort of, you have to take my word for this one, and then I will connect my original, the fermion systems that I'm talking about with this.
Okay, okay.
So this is something you can take it as a theorem for now, okay? That this happens if you are given a Euclidean fermion operator with this property, then there is a current.
Right.
What this fermion operator is,
yeah.
How this is connected to the system that I'm talking about, that I'll come to.
I guess on this slide, should I imagine there's a defect present or no defect present?
Oh, there is a defect.
There is a defect.
There is a defect.
Okay.
Yeah.
Okay.
When you say defect point-like, you mean point-like in space-time?
Yes. Yes. So this current that I'm showing, so the bulk here is both space and time.
So then it's an operator, right? It's just an operator.
Yeah.
But isn't it the same thing like Cullen-Hardy effect, like the anomaly flow from the bulk effect?
It's a little bit different in the sense that in the time direction there's no flow. Here the current is going to flow from both time and space to the defect. So the last 3 lines that I wrote, that there is a current and that its space-time integral of its divergence is 1, this is something that requires proof, and I'll get to it hopefully in the second part of the talk.
Can you give an example of in a model where this appears? Like,
So this is the construction that I'm going to show. It's going to happen in all models.
I see. All of them will have a point-like
Yes.
defect.
Wherever. It's more general than this, but I wanted to stick to open space-time with a point-like defect. Okay. So I have to clarify a little more here. So if I call that Euclidean fermion operator dE, and its conjugate transpose dE dagger, then for the current to exist, either dE or dE dagger should have a zero mode, not both. So if dE has a zero mode, then current flows towards the defect. If dE dagger has a zero mode, then current flows out of the defect. If both of them had zero mode, then you wouldn't have a net current. Okay, so it's either dE or dE dagger should have a zero mode. And so here, what I'm really saying is that since the number of zero modes of dE minus the number of zero modes of dE dagger is just the index of the operator dE, in order to get a non-zero index and a non-zero current, you need, in order to get a non-zero current, you need a non-zero index, really. That's what you need. So it's not enough to have a zero mode for DE. You really also need no zero mode for DE dagger in order to get the current. So now I come to the question that Nabil was asking. So what is the connection of this Euclidean operator with the original massless edge states that I was talking about? So consider a Minkowski fermion operator D with mass defect in space. So D lives in all of space-time, okay? And so let's say this is the mass defect, and you have some massless edge states living on the defect. And so these states are, of course, normalizable in the direction transverse to the defect. They're not normalizable along the defect coordinates. For example, they're not normalizable in time. And these massless edge states are, of course, zero eigenvalue eigenstates of this operator D. But because they are not normalizable, they are not zero modes of any operator. So at this point, I don't have any generalized Hall current. Okay? So now let's go to Euclidean space. So I take this operator D and I write down the Euclidean space version of it. And I'm going to now construct another fermion operator in Euclidean space, which I call F. And sometimes I'm going to call it DE. And it's going to depend on some scale mu. And to write down this operator, all I have to do is to turn on some background field of strength mu. Okay? The only requirement here is that f of mu approaches D as you turn off the background field. Okay? So in the limit of mu going to 0, f matches with the Euclidean version of your fermion operator. There's no requirement at this point on this background field to be allowable in the original theory. Okay? But eventually you will see for the problems that I'm interested in, where I want to distinguish between gappable phases from gapped phases, or gappable fermions from gapped fermions, this background field is going to be allowable in my original theory. But for now, it's not a requirement. I also have to keep in mind that when I turn on this background field, that f has a zero eigenvalue eigenstate normalizable in both space and time for any mu, no matter how small mu is. So this is something I have to engineer, and it's possible to engineer this. So f has a zero mode for any mu, and it has a non-zero index that survives in the limit of this background field going to 0. Now the important point is that the zero mode is going to be absent if the original fermion operator did not have massless states to begin with. Okay? And it's going to be present if and only if the massless edge states existed for the original fermion operator. So now there's going to be a generalized Hall current for any mu, and what you will see is that its space-time integral of its divergence is going to be a topological invariant. It's going to depend on a winding number, which is going to survive in the limit of background field going to 0. So here's an example for 2 slides, and then I'll jump to the particular example of Majorana chain in 1 plus 1D. So how to construct this operator f of mu? This I'm doing in 3 plus 1D. So this is a 3 plus 1D topological insulator with 2 plus 1D bulk states. 2 plus 1D surface states. So that's described by this 3 plus 1D Lagrangian here. And so my fermion operator lives in all of space-time. And if I wanted to look at the spectrum, low energy spectrum of this fermion operator, I would just get this massless states on the boundary, right? And what you see here is that if I pick a random state here, it's a zero eigenvalue eigenstate of my Minkowski fermion operator, right? But if I now go to Euclidean space, they are not. So these random states on the Dirac cone are not zero eigenvalue eigenstates of my Euclidean operator. But this one still is, right? So this is exactly at 0. But it's constant in defect spacetime. It's not normalizable in the defect directions. So now I would have to introduce some background field to make this completely localized to a point-like state. And so now we have F. So that's how we construct F. Some clarification here. I'm not claiming that my original fermion theory has a generalized Hall current. I'm not claiming that. Claim is only if my original theory has massless edge states that there is this generalized Hall current in this construction. The current by itself will not tell you anything about symmetries of the original theory. It will only count the number of gapless modes given a particular theory.
But isn't that the same thing like constructing the eta invariant in some sense?
I don't think it's the same, because when you do that, so I'm saying that even in a theory where you could, in principle, have gapped fermions, the probe that I'm putting in is going to tell you whether you have gapped fermions or whether you don't have gapless, don't have gapped fermions. And I don't think that's the role eta invariant will play for you. It's a different role, I think. Okay.
But Sri, I mean, one thing that confuses me, everything you're telling us is about tree level mass.
Yeah.
And those we can always add. And you know, so I mean, the real question is how you gave this example of mod 8 anomaly, which you need some self-interactions of fermions, and these are really tricky.
Right.
Why do you think that your method will answer anything about those?
So there is a, so let's say you are doing the 1 plus 1D calculation with the 0 plus 1D edge states. On the boundary of the 0 plus 1D, of this 0 plus 1 dimension world, you can compute the number of degenerate ground states. And it's a simple quantum mechanical calculation. And what you can see is that I can take the background field that I will introduce, and I can then compute what is the spectrum on the boundary when I have this background field. So that includes the interaction and includes my background field.
But if you have for Fermi interactions, I mean, the relevant thing is not the Dirac operator.
Yeah.
Theory
Yes.
is difficult to compute.
Yes.
Why do you think that, you know, this
so the picture that I'm showing you is for free theories, but I will give you a definition for my generalized Hall current, which holds both in interacting and non-interacting theories. And the question is, if you compute the space-time divergence of this current in an interacting theory, it should give you 0. That's what the hope is. Even though so in that case, it won't tell you about free fermion propagators. It will tell you about the interacting theory. How many degenerate ground states you have, for example, on the boundary. Okay, and another thing that I want to point out is that I don't think, in general, when people think about global anomalies, I don't think the connection between bulk and boundary in that case is perturbative at all, right? So in that sense,
not necessarily, but yeah.
So for example, I don't think that's the case in 1 plus 1 dimensional example that I'm showing you. And you know what you see here for this particular construction is that it's completely perturbative for free theories. You know, that connects bulk to the boundary. It's a curious fact, I think. It's not useful for anything, but something interesting, I think. So here's how it works. So let me tell you how to construct this operator in the 1 plus 1D Majorana chain example. So I'm considering the continuum version of Kitaev Majorana chain. This is my Minkowski Lagrangian. And so these psi are Majorana fermions, and C is some charge conjugation operator. So now I can write the corresponding Euclidean Lagrangian, which looks like this. And if I have a step function in this Majorana mass, the defect was Majorana edge modes, right? They are Majorana zero modes. So of course, in this theory, I don't have any conserved current. If I'm only looking at one Majorana fermion, and there's no chirality on the defect, so there's no Hall current-like picture, obviously. So now take this Lagrangian and extract the corresponding fermion operator. And I'm interested in zero eigenstates of this fermion operator, right? So the zero eigenstates of this operator are also zero eigenstates of this operator, if you get rid of the C. So let's work with the zero eigenstates of this operator. And what I'm going to do is I'm going to replace my Majorana mass by a field for now. I'll call it phi 1. And you'll see why I'm calling it that. So now if I solve for the edge states, what I see is that, okay, so in phi 1, so in this field phi 1, I have this domain wall where m0 is greater than 0. And this epsilon is a step function. And this operator is really d dagger, so it's a typo. And if I solve for the edge states, what I find that there are two edge states, massless edge states for d and two for d dagger. And none of them are normalizable in the time direction, of course, right? I don't have any mass term in the time direction. So none of the solutions are normalizable in the edge coordinates, so my index is 0, so there's no generalized Hall current at this point. Okay. But now I'm turning on my background field, and the background field that I turn on looks like this. Again, for when I'm dealing with one Majorana fermion, this background field does not exist in my original theory. But remember the construction I told you, which is that only if my original theory had massless states, that in my constructed theory, I will have a zero mode, okay? So I'm turning on this background field. This has a step function in the time direction, okay? And it's proportional to a scale mu0, and this mu0 is greater than 0 for the purpose of this analysis. And now I can look for edge state solutions. So note that in the solutions, one thing that I find is that one of these states, which were eigenstates of the operator d with zero eigenvalue, becomes a zero mode. So it becomes normalizable in space and time. And the other ones are not normalizable anymore. I mean, they were not normalizable before either, so they remain non-normalizable. So I end up with a non-zero index. Okay.
I have a question. I think it's a stupid question, but I'm worried about the factors of I. This was a Majorana mode, and usually there's a basis where the Dirac operator is real.
Mm-hmm.
But here, that's not possible when you introduce the second field necessarily from the line.
Yes. So this is a Dirac operator corresponding to the original Majorana fermion theory that you had. And so I can turn on two mass terms. One is a pseudoscalar mass term, and another is a standard Dirac mass term. And the claim is that if you have a cross-domain wall in those two mass terms, you can get a zero mode. Yeah, and this is again in open space.
So you are enlarging the fermion representation.
Sorry?
You are enlarging the fermion representation.
Yes, exactly.
It's still real though, from zero.
So what?
I mean, it's going to take it out of the real, right? If you act with that operator, it's not going to be real anymore.
So
Or
it's,
the real
both of them are mass terms, right? So if you look at for example, the propagator, it looks like 1 over p squared plus phi 2 squared plus phi 1 squared. So if you turn on a phi 2 term, it's like a mass, so it will your states will exponentially decay. Same with phi 1, your states will exponentially decay. Because both
Can
work.
you remind me of a really basic question? In 1 plus 1, if I have a Majorana fermion, is there a complex mass for a Majorana fermion in your
No,
signature?
no, I don't.
There's not a mass in a gamma 5.
No, I don't think you can do that.
So you are effectively doubling the Majorana
yeah,
and making a complex fermion.
Yes, yes, yeah, yeah.
But such states are gappable.
What do you mean?
I mean, you started with. I thought you wanted to study the Majorana fermion stuck on the domain wall,
Yes.
which is not gappable.
That
It's
is
just
not
a-
gappable.
Yeah.
But what I'm saying is,
But you modified the problem. Now you have two.
yes, yes, yes. I'm just saying that only if you had this original massless Majorana fermion, a single massless fermion, that in this construction you will have a zero mode. If you didn't have the original one, then you wouldn't get a zero mode here. So the chain of logic is one way, flowing in one direction. Okay.
Okay. But at this level, this is not saying anything more than the anomaly, right?
No. And so I will discuss the two Majorana case where you will see that I actually don't have to enlarge the space and that the background field, you can accommodate it in your original theory itself.
So said a bit differently, there's an extra U1 symmetry in this problem.
Yes.
And the phi
Yep,
is
yep,
basically winding.
Yes,
Two steps
yes,
are
yes,
winding
yes,
phi.
yeah. I mean, basically, when I have this phi1 term, I can actually do a chiral rotation on this and get the entire mass on the Dirac mass thing, and the entire story just follows. But yeah, when I have a profile, space-time profile, then I won't be able to do it everywhere in space. This chiral rotation to get all the mass in the Dirac term. Okay, so this is what happened. Originally, I had states that were localized only in x1, they were not localized in x0, but I turned on this phi2 field, and now one of them is localized everywhere, and this is the zero mode that I'm talking about. So if I take the mu0 to 0, I recover the original fermion operator, as I said. Index is non-zero for any small mu0 in the limit of mu0 going to 0. And I'm going to take, for all the examples that I'm going to discuss, I'm going to take this limit of mu0 going to 0, because that is really what is going to tell you between gapped and ungapped fermions in your original theory. So as David was pointing out, that there is a vortex in this problem. So I'm just elaborating on that idea. So a cross domain wall, as I showed you, can be thought of as a vortex. And if you look at the zero mode solutions of your fermion operator, what you see is that for the particular sign of the domain walls that I took, I found that DE had a zero mode, DE dagger didn't, so I had an index of 1. If I flip the signs of both the profiles, then again I have a zero mode for DE, and DE dagger doesn't have 1. So again I get an index of 1. If I flip the sign of either one of them, then DE dagger has a zero mode and DE does not. So I get an index of -1. And this can be sort of rephrased in the following way. So I can create a complex variable by combining the two mass terms. And I can write it as a radial term and a phase term. And what you can see is that if you have a domain wall, cross domain wall profile like I showed you, then this phase winds by either +2 pi or -2 pi, depending on what the signs of phi1 and phi2 domain walls are. And the center, so this is exactly like a vortex, or close to a vortex, with the core of the vortex at the center of the cross domain wall. So this is the reiteration of the same fact. If mu0 and m0 are both greater than 0, alpha winds by 2 pi. If both are less than 0, it winds by 2 pi again. But if they are the opposite signs, it winds by -2 pi. So what you see is that the index equals the winding of the angular variable. And so the claim is that there is a generalized Hall current flowing into or out from the defect, depending on what the winding is. again, the number of massless edge fermion in your original theory is the index. And the winding survives in the limit of mu0 going to 0. This is another way of saying the same thing. So what I'm trying to show you here are the two domain walls. And the winding survives taking the mu0 going to 0 limit, because the only way to remove the winding in phi 2, or the only way to remove the winding is to destroy the domain wall in phi 2. And so as long as you have a domain wall in phi 2, as you take the mu going to 0 limit, the winding remains. You can do the same thing with the domain wall in phi 1, the Majorana mass. And again, as long as you have a domain wall in the Majorana mass, you get a non-zero winding. If you could destroy the domain wall in the Majorana mass, you wouldn't get any winding, and so the index would go to 0. So now look at a multi-flavored free theory. So here, I and J basically tell you the number of flavors in your original theory. So again, with a domain wall in mass, there are NF fermion flavors, let's say. And in principle, I can write a mass term coupling these different flavors, which gap these edge states. But I can write a certain T-reversal symmetry, which I will show you in the next few slides, which can prohibit these mass terms. So I get as many massless states as I had, or the number of as many number of flavors I had in the original theory. So the corresponding index is NF. It can be 1, 8, 13, 55, whatever you want it to be, because this is a non-interactive theory.
Sorry, did I understand correctly the logic? So you have a Dirac operator acting on some fermions, and then the rules of the games are, let me modify the Dirac operator and potentially modify the space on which it acts, doubling it maybe?
Yes.
And consider background fields I can put. And the claim is that if I can put background fields such that this Dirac operator has a zero mode,
yeah, in the limit of background field going to 0.
Is gapped.
In the limit of background field going to 0.
Yeah.
Then that
Yeah.
means that you, in your original theory, you had massless fermion. So this becomes interesting in the two
by
flavor
massless
theory.
you mean you didn't put the mass explicitly because everything is free.
Right. So now, in the two flavor theory, I will put in a mass term. Again, it's a free theory mass term. And you'll see how that works. So let's take two copies of the Euclidean Lagrangian that I showed you. And again, with the domain wall in mass, there are two Majorana edge fermions that are massless. I can combine these two Majorana fermions into a single Dirac fermion theory. In this case, I will not have to double the number of degrees of freedom that I have, because I'm just going to extract a Dirac fermion from the two Majorana fermions. So this is my Lagrangian now. Psi is a Dirac fermion. All right. So again, this is a two-flavor theory. If you did not have mass terms turned on that would couple the two Majorana fermions, you would turn on background field, like I said. In this original Dirac fermion now, you would turn on a background field here. And you would get an index of +1 or -1, depending on the winding in this field. Now, to count the number of massless Majorana fermions in this case, you just have to multiply the index by 2. And again, if the index and the current survive this limit of mu going to 0. So now I am going to turn on a mass term that couples the two Majorana fermions. So let me define a particular T-reversal symmetry, which is like this. And with two flavors, I can write a T-reversal breaking mass term, which looks like this. Okay? This will gap out the two edge states. And so in that case, I should get an index of 0 and a 0 generalized Hall current. So how does that work? So this is what happens. So if I take this mass term and write it in my Dirac fermion theory, this term looks like the background field term that I was introducing, okay? And again, note that in this example, I haven't doubled the number of degrees of freedom. I just have whatever number of fermions I had in my original theory, okay? So this looks like the background field term, and this is constant in space-time. So now, given this theory, now I'm going to turn on my background field, which had a step function. Okay, so this is my new Lagrangian, which is going to probe if I had in my original theory, massless modes or not. So now, if I look at the edge state solutions of this, what you can see is that I have one normalizable solution for 0 eigenvalue state for dE, only when this kappa, this mass scale that I put in, gapping the two flavors, is smaller than the background scale that I put in. Okay. So this is non-zero only if kappa is smaller than mu 0. So in this case, the index depends on the winding of this combined field phi 1 and phi 2 plus kappa. So the domain wall in phi 2 plus kappa exists only for mod kappa smaller than mu 0. It's gone otherwise. So as I said earlier, that I would take mu 0 going to 0 limit in every case. The winding doesn't survive because the domain wall doesn't survive in this extra, in this time direction.
Sorry, but what if you kappa is just a parameter?
Yes.
Set that to 0, and you still have a mass. There's still gap.
No,
and
no. If you set kappa to 0, there is no.
But you have an explicit mass, didn't you?
No.
Sorry, there was an M. I thought I saw an M.
That has a domain wall.
Oh, sorry. Sorry. Never mind. Okay, that's the domain wall profile.
Yes. So I'm counting the edge states, right? So I will always have a domain wall there. So this is the scenario that I'm babbling about. So this is the phi 2 equals 0 line. This is where, let's say, kappa lives. Kappa is greater than 0. And now let's say I turn on this background field in phi 2. As long as the height of the domain wall in phi 2 is greater than the scale kappa, I have a non-zero winding combining the phi 1 domain wall and the phi 2 domain wall, or phi 2 plus kappa domain wall. But as I take the height of the domain wall smaller than this kappa scale, I have lost the domain wall and my winding is 0.
So kappa is the mass on the domain wall, basically.
Yes.
Acts as a mass.
Yeah, you're gapping out the two Majorana's. Yeah, with a term like this.
In kappa hits u0, this 0 mode becomes non-normalizable.
That's right. Yep. So some observation for this two-flavor theory. The index is 1, so the corresponding number of massless fermions is 2. If I choose to preserve the T-reversal symmetry. So if I don't break it, I get an index of 1, so that just tells you have gapless 2 Majorana fermions, which is not the same as gap 2 Majorana fermions. So that's what is the first line. So the index is 0 if I break the T-reversal symmetry. The difference in the value of the index depends crucially on this limit of background field going to 0. So at this point, I can take a break, and I will tell you how to construct the generalized Hall current, given that I have this operator with a non-zero index.
All right, we'll have a short 5-minute break, and we'll be at 11.
don't know
actually
much
confused
about
about and the messenger. Okay, I mean, or now, basically, the first one you have to identify your global sentences. Okay, and then you can ask the question whether actually you can have a master or whether the theory can be gapped.
Yeah.
Okay, without explicitly breaking your global sentence.
That's
So
right.
the idea is that actually
So these just get some, you know, minus j energy, and the rest is 0. So then would off-diagonal term
It is actually an
be
anomaly.
some sort of
Then you cannot, you cannot gap your theory. Has to
Vanish,
like
that's right.
But what you are doing is different from that, right?
Yes, yes.
So,
So,
and that
if,
also,
so imagine the
they
case
should also
where
come with.
your anomaly vanishes. Anomaly
That's what
cancels.
I don't know if.
okay, so
Let's go to that
They
case.
will all be permutations.
By the way, I haven't worked out
conserved,
that here. That's the hope
Some
we're
color
hoping
numbers,
to
right?
apply this eventually.
right.
Let's
And then,
say you are in
but then are they
a
also, all
thinking
the
about a
matrix
case where anomaly
elements would
cancels.
also be
And so
negative?
let's say you have a bunch of fermions, you could possibly get them out by turning on symmetric interactions.
Exactly.
So in that case, you might have to tune your parameters to go to a regime where these fermions are gapped.
That is correct, yes. Of
Right.
course, you have to introduce some operators in the theory so that you fly
Right.
the risk that
Right.
right.
And so there's going to be two regimes where the fermions are gapless and another where they are gapped, depending on what you're determining.
Right.
And so what we're hoping is that the index that we are computing, in fact, the divergence of this generalized Hall current,
It's like
that's
an
going to be
antiferromagnetic
1
yeah.
or non-zero,
Okay, so then you
some
should
integer in the
give
limit
plus
where your original
okay.
fermions were massless
You should
and anomaly was cancelling.
Right. So then
And
you should
it's
give,
going to be
you
0
should have
in the
one
limit
with
where
all
your
different
fermions
colors.
got gapped. Again, anomaly was cancelling. So the anomaly cannot tell between the gapless and
No, I
gapped.
realize, I was just confused now when I thought, of course
So
it's,
this is just going to
all
tell you
unequal
the
then
hope
you
is.
Because
But
this
then the
index, okay, every time you
off-diagonal
talk
term
about
should
an
be
index, this is
some
like a
sort of
Walsh
permutation.
and whether the theory, okay, will
So I
go
think
to a
the
massive regime or not,
correspondence to the
this is,
JQ model
this
here
is a
would be,
dynamical
you
question.
should
Yes,
not
yes,
have any
yes.
two
So how an
body
index
term
can
at
tell you
all.
about
You
So-
just
about
have these
dynamical
three
thing.
body terms.
Right,
And then
so
you make
it's-
few terms of this
Eventually, so
fraction
what
of
I'm going to,
product
in the
of
free case, I'm going to relate the index to d mu, j mu
exactly, that's what I think.
of some
And,
current.
but what I don't know is
And this
if,
current
since
is,
I don't know
this
the
quantity
details about
is,
SC3 in the representation you're
is
using, I don't know
definable
if all the
in
matrix
free
of
theory
time
or in
chronal matrix elements
So
would be
it
negative.
may or may
because
not
if they
equal the
are all
index.
negative,
Okay.
then
So
we
this
can do
equals the
QFC
index of the
simulation.
fermion operator for free theory.
Right.
The hope is that when you have the
I guess you could ask
interaction,
me.
then it's not going to equal the index
Uh-huh.
of the fermion operator. Except that it's going to tell you how many
Right.
degenerate ground states you had.
Yeah, and if
on
we
the
consider
boundary.
everything out of that.
So it's going to, basically when you turn on
then
interactions,
Yes, I guess no more. You could
this
ask it in a different
mu,
way. If I
and
propose,
interactions, and let's say your
this kind of
fermions,
Hamiltonian,
massless fermions
does
are
that
gapped,
for SC3,
then this is going to be zero. That's what we're hoping.
I see.
And you can compute this in the interaction.
If we construct
And
out of
if you
single
have a regime
projector,
where interactions did not gap,
Yeah, that's what I thought. And the singular projector should
then
be
it's
just
going
the
to be
sum of
whatever
all these unequal.
number
Yeah,
of
yeah,
massless
right.
fermions you have.
Right.
I
Yeah.
see.
Can you
We haven't
tell me what
proved
the
this yet,
archive
but
number
this
is?
is
Oh,
fine.
yeah,
You
you are
have to
telling me that
update
this integral actually is not at the Walsh invariant.
Yeah.
Right. It's,
Uh,
it is an RG
so-
variant quantity.
So
Zero,
there are reasons to believe that it's an integer.
One.
Yeah.
Okay, I will look it up.
Yeah.
But if it is a
Yeah, then if you like, maybe when I read your paper, I can send you some email.
Oh, that's great.
Looks really interesting.
And so we are hoping that
If it has more of
only,
the kinds of defects, I guess there can be some
the
exciting.
contribution of this mu j mu will, for example, for the Generalized case, are going to come from how many
Right. Yeah, and I mean, especially if we
uh,
actually would be able to
Mass
simulate it, then we can really look at it in detail. So what did you do in your paper?
For the case of a neuronal interaction, it's immediately gaps everything. So there's no keeping of
But again, in order to distinguish which phase you are in, you actually have to see the posterior.
That's right. Yes.
So there's no way that you can do this computation until whether you.
That's right. But what I'm trying to do, I'm going to eventually do this on the lattice.
I see.
And I want to count how many gaps fermions.
But they didn't tell you any large
What I'm
scale
saying is that you can
calculation.
compute on what is
Okay, that
sits
would be
on
really
the bulb.
nice if you could.
And if you are in a routine where you're getting some integer NF, that means, oh, you haven't been able to gap. And so you compute it non-motivatively on the lattice.
Thanks.
I think we can resume.
Okay. So I don't have too many slides after this. So I think we've done pretty early, and then you can ask me more questions if you want. So given a non-zero index for the fermion operator, now I'm going to massage it to write it in a different form. So my claim is that if I define this variable I, which depends on some mass scale m, the following formula in the limit of m going to 0 computes the index of this operator d. So this term counts the index, this term counts the number of 0 eigenvalues of the operator de. This term counts the number of 0 eigenvalue modes of de dagger, and so this gives you the index in this limit. So now I can rewrite this formula in terms of some higher dimensional matrices. So I define this matrix K, which is related to my original, or rather related to my fermion operator with non-zero index in this following way. So it's twice the dimension of my original DE fermion operator. And I also define a gamma 5 matrix, which also has twice the dimension of DE. And my claim is that this formula can be written in terms of this K matrix and this gamma chi matrix in this way. One interesting thing to notice is that the K and the gamma chi that I have defined, they anti-commute. Okay, so it's like I can think of this K as some kind of a higher dimensional fermion operator, which has some chiral symmetry if you don't have a mass. Okay, and so in this formula where I'm relating the index to this operator m plus k, this 1 over m plus k itself looks like a fermion propagator, right? So this looks like a fermion propagator, but it's a higher dimensional fermion operator, okay? It's, for example, let's say if you think about the Majorana example, DE was living in two space dimension. So I had polymatrices appearing here. But now K is 4-dimensional. So you can almost think of this as a 4-dimensional fermion operator, except that it only has this 1 plus 1 space-time derivative. It doesn't have a space-time, derivatives with respect to the third and the fourth dimension. Okay, so that's what it looks like.
Sorry, I didn't fully follow, the operator there has both the bulk and the boundary?
Yes,
Okay. And the domain Wolfram.
everything, yes. Okay, so M plus A looks like an inverse fermion propagator on a higher dimensional theory. And I can compute this I of M, this quantity, in a path integral where the action is given by this formula. So K plus M is my some fermion propagator. And I compute the trace of this psi bar gamma chi psi. So psi bar, when I contract, I get the corresponding inverse fermion propagator or fermion propagator there. So that just equals this quantity without taking M to 0 yet. So it's just this quantity. Okay.
So is there any derivative for the extra coordinate?
No.
I see. So just the matrix structure?
Yes, just the matrix structure. And it's important to remember that I have to integrate, when I write the action, I'm integrating over space-time of my original two space-time dimensions, okay? And so as a result, this field psi, on which I'm doing the path integral, it also depends on my original space-time dimension, does not depend on the third and the fourth coordinate. So eventually, what's doing is that it's you have some extra flavors of fermion. That's what's going on. But this is an identity, or rather, this is an equal sign. So every time I have an operator DE with a non-zero index, I can compute the index, or rather, I can compute this particular variable I of M, which is related to the index in this higher dimensional theory, where my fields don't depend on these extra dimensions. So what you see here are these spinors, double the size of your original spinors in your original fermion theory. And if you take the limit of M going to 0, this theory has its own chiral limit. Okay? It's also, you can think of it as a flavor symmetry instead of a chiral symmetry. Okay? Okay, and you can get the corresponding gamma matrices. You can read them off by looking at this K. And in this theory, I can define an axial current, which is just psi bar gamma mu gamma chi psi, and try to see what its ward identity is. And you see, just do the standard chiral transformation, and you see that space-time divergence of this current is related to 2m psi bar gamma chi psi, which is this operator Im. So if I take the M going to 0 limit, this is nothing but the index, right? So that's what I started with. So this is what we wanted. The divergence of the current, of this axial current, is related to the index of the fermion operator. Now I just want to point out for those who are wondering is that I can actually I can very well define this current even in an interacting theory. And in that case, this d mu j mu is not going to correspond to the index of the corresponding fermion operator, especially if your massless edge states are gapped. But the hope is that in an interacting theory, it's still going to tell you how many massless edge states you have in your theory. So hope is that if your boundary was gapped, this d mu j mu would give you 0.
So your current G mu is the current in D plus 1?
Yes, that's right. So this mu goes over 0 and 1 in the Marana example. So it has 2 dimensions.
So just to understand the statement, in the Minkowski-Kitaev case, you had 8.
Yes.
But would you think this would give 0?
That's right.
So this is an index. It's a U1 value index.
That's right. So yeah. Yeah. So if you remember what I did for 2 flavor case, I turned on. So I wrote them as a single Dirac fermion, and then I turned on a background field there. So when I have 8 Majorana fermions that are free, I'm supposed to get an index of 4, right? And so I have to multiply the index by 2 to get how many Majorana fermions I had in my original theory, massless Majorana fermions. And our hope is that when I turn on interactions, then this d mu j mu is not going to give me 4 anymore, it's going to give me 0.
How do you propose calculating this in an interacting
Yeah, so that's what I was discussing with Mohammed a little bit earlier. So I'm not saying that you should calculate it perturbatively when you turn on interactions. So if you remember what the original motivation was, I want to take a lattice theory and I want to see whether I have gapless fermions or whether I have gapped fermions. When you turn on these interactions, you have to tune to go to a regime where you have gapped fermions. So let's say this is your lattice, and this is where your gapless or gapped fermions live. And now you have turned on interactions. All I'm saying is that you can compute this d mu j mu in the bulk on the lattice when you're simulating it.
But you need to double the degrees of freedom. You're not simulating the same theory anymore.
That's okay. That's fine. Take the same theory in terms of interactions, double the degrees of freedom. They don't talk to each other when you double the degrees of freedom. And just compute this current, the axial current, in this theory. And every time you tune parameters in order to get to a regime where the corresponding axial current is 0, you say, okay, I have gapped out my original fermions.
It depends on what interactions you take. For example, let's say that you have some you have some dynamical gauge fields which interact with your degrees of freedom. You double them; these interact with the same gauge fields, so they do interact with each other. So that's not the same theory. So maybe if you just have some fermion interactions, and then you can just double them so that they don't interact. But it's not clear that you can do it always. You understand what I mean?
Yes, I understand. And that is something that we are hoping to get to. It's not something that we have constructed yet. But that's really what the motivation is. Yeah.
The second question, I guess, is why do you have this hope? Because so far you gave us like
Yes.
fermion. Is there some deeper reason to think that this will hold?
So you can explicitly calculate the spectrum of your edge states in the 1+1 decays. With the 0+1 d edge states, you can explicitly calculate in the sense you can do a quantum mechanical calculation. And you can see how many degenerate ground states you have in that case when you turn on interactions versus when you don't turn on interactions. And you can, even though, so it's a pen and paper calculation, basically. And you can turn on the background field that I'm telling you, and in the presence of interaction with the background field, you can look at the spectrum in that case. And what you see is that the background field affects the spectrum on the boundary in a way that we want it to. So basically, we were looking at states that decay in time, right? And so what you see here is that there's a competition between the background field that you're turning on and the strength of the interaction that you put in. And whether you have decaying states in the time direction or not depends on whether this background scale is larger than the interaction that you put in. So as soon as you take the limit of background field going to 0, you lose this decaying states in time. And only you get these decaying states only when mu is large compared to your strength of the interaction. So that gives us hope that the current that we are computing, first of all, we have to prove that the current we are computing gets contribution from the states that we are looking at. So we looked at basically spectrum on the edge. So we have to prove that in the interacting case, that's where d mu j mu gets all its contribution from. But provided that happens, we have reasons to believe by just looking at the spectrum on the edge that as you take the limit of background field going to 0, you lose these decaying states in time.
But in the presence of background field, since your background field has a kink in the time direction, right? It's not time translation invariance.
That's right.
You can't really define a Hamiltonian in this case. You use that. And I'm wondering what do you mean by the spectrum? If I don't have a Hamiltonian.
That's right. So first of all, I'm going to Euclidean space. So time is same thing as space when I'm going there. And so, you know, in I guess my Hamilton, well, a Lagrangian would look something like this, right? And so I can solve, you know, I basically diagonalize the Hamiltonian, for these gaseous fermions, or these fermions. And what I do is I put in, now when I have these 8 fermion states, I will have I will write the corresponding complex fermions, and I will be able to turn on, you know, a step function perturbation in time for them. And that just looks like, you know, it looks like sort of like a cosmological constant term being added to the Hamiltonian. That's what it really looks like.
So basically,
And so it's a step function in cosmological constant.
a series of Hamiltonian equals a different.
That's,
You
yes.
see what's the behavior.
That's right. Yeah, so if you looked at the Hamiltonian in Minkowski spacetime, then what we are doing here by turning on this background field would look like a time-dependent cosmological constant. And so that affects the spectrum. I mean, the spectrum in the sense that affects, when I look at the sort of the diagonalize the corresponding Hamiltonian and look at the states, I find decaying states because of the step function in the cosmological constant. But
Sorry, one more time. So if you are saying that if the theory is gapped, then the integral of the current, of the divergence of the current is 0?
that's the hope. I have not yet connected.
Yes, but this is the hope, yeah.
This is
If
the hope.
theory is gapped, you get 0.
That's right. That's right.
I have just one more question. Is that easier because you have to measure it on the lattice anyway?
Yeah.
Is it easier than just measuring on the lattice where you have you have gapless state? Look at correlators and look how they decay.
So I think that it might be easier to look at stuff in the bulk as opposed to right at the boundary where you measure the correlators.
But you don't have to put. I mean, if there's degrees of freedom which propagate on the boundary, you can take. I mean, you can take even correlators in the bulk if they're just sufficiently close to and along the boundary.
Right, but if
There's going to be some signal there.
But if you have gapless fermions that live on the boundary, and you want to be able to detect them, I think you would want to measure correlators on the boundary, right?
That's right, but there's going to be some correlators to the boundary which are exponential, and you know there's going to be propagators along the boundary.
So
I mean, yeah, you can measure them on the boundary. That's fine, but
so I think this is going to be cleaner because it's away from the defect. So that is something I'm working on with someone to see how clean this is. Like when you compute the divergence of this on a lattice, how close do you get to 1 when you have massless modes? And then when you turn on interactions, again, how close do you get to 1 if you don't gap out the fermions in the boundary? And so far, it looks like that this is really clean if you're sufficiently far away from the boundary. So that's all I can say. I mean, we haven't measured correlators on the boundary because we don't even have interactions at this point. So that is something I will have to see how good this is versus turning on just directly measuring things on the boundary.
Can I ask a question? So when anomaly is, for example, mod 8 or mod some finite number, then one way to match that anomaly is, of course, having a massless fermion, but another way is having some degenerate ground state with gap to degenerate ground state or topological order.
That's right.
And so in that kind of situation, so
right, what happens?
to this?
Yeah, so I'm hoping to connect this to a theory where anomaly cancels, right? Eventually. Because I want
They want to gap the mirror fermions, so they're hoping to use this as a diagnostic tool when fermions are gapped.
I see. So in the case of topological order matches the anomaly in flow, then system itself is gapped, right? Although there is some
We want a case which has no anomaly, where
Right.
you can gap them trivially, and
I
check whether they are gapped then.
Okay, I
And this is a diagnostic tool they're proposing for that scenario.
right.
Because otherwise you have no chance of having a chiral gauge theory. You have to cancel all anomalies.
That's
Okay, yeah.
And yeah, and the other thing is you have some kind of correspondence between bulk and boundary, which might be interesting to you, which is different from what you see in anomalies. Okay.
But presumably, I mean, for Yuya's case, you would still, even when you have an anomaly, would it give zero? It is a good question. I mean, because you're saying it's a diagnostic tool for whether or not
there are gapless states of
there are
fermions.
gapless states. You're not saying that it can still be a non-trivial, spontaneously broken discrete symmetry
That's
state,
right.
So it is.
I think we are limited to counting gapless states of the in how many. For example, if you were computing explicitly the fermion correlator, which you can do even in an interacting theory. And so the question is that gapless or not gapped? And I believe that is something that we'll be sensitive to by doing this computation. That is sort of that is what I can say by looking at how we constructed this whole, this is psi bar gamma mu gamma chi psi, and now our hope is that that's what it is sensitive to, the fermion spectrum.
I have another question, but maybe I should let you continue so that Nakarin doesn't stop me.
Yeah, it's okay. Either way, I think it's.
I'll ask later.
Okay. So, because I'm dealing with free theories, I'm just going to compute J mu chi explicitly in this diagnostic background field by treating the diagnostic background field as perturbation. And I'm going to do a one-loop Feynman diagram to show that its space-time divergence reproduces the index. So this is the K-matrix for the Majorana case. And you can see something interesting here. So this is the gamma mu d mu term, where mu goes over these two space-time indices. And you see the two background, the Majorana mass and the background field that I turned on, they kind of appear like a gauge field in my double theory. But none of the fields have any dependence on the third and the fourth dimension. And so, so the question is, how do I set up this perturbative calculation? So note that the index, as I showed you for the Majorana case, was dependent on the winding of this phi 1 plus I phi 2. And so what I'm going to do is that I'm going to expand the fermion propagator in the angular variation of this combination. So it's just, this cross-domain wall, what I'm writing is, the spatial variation of the corresponding vortex profile and the angular dependence as well. And so you can expand k in some k0 plus delta k. So this is what you get when you expand in rho and alpha. And I will treat alpha as slowly varying because I'm going to be very far away from the core of this vortex or the defect. And so that's my current, right? Psi bar gamma 5 gamma mu psi. Here, when I contract this psi and psi bar, I get the full fermion propagator, right? And so I just expand this in this, term alpha or delta k, and it looks like this. So I just have this one external line of alpha in this fermion diagram. And if you do this, compute this diagram, you get this nice expression. And of course, this is just proportional to the winding. If you compute the space-time divergence and then compute the space-time integral, you get the index that you were looking for. So now I want to ask a different question, given that I have reproduced the index. The question is, why is the momentum space integral of this certain Feynman diagram producing a result that is quantized? So, okay, I'm getting this d nu alpha from here, but if you combine everything else, why does it give me 1 over pi? This particular trace produces an epsilon mu nu, but why do I get a 1 over pi? You could ask this question, some random Feynman diagram. And you can ask a similar question that was raised in the case of lattice quantum Hall effect, both in the case of relativistic Dirac fermions and 2D electron gas, where you can compute the Hall response using a one-loop Feynman diagram. So in the lattice quantum field theory, it's just a one-loop lattice perturbation theory diagram. And so what you see in that case is that in this lattice QFT, for the quantum Hall effect setup, as you tune the parameters of this lattice theory, the corresponding Hall coefficient can jump between 1, -2, 1. It's always an integer. And it comes out, you can compute it in a one-loop Feynman diagram, the entire calculation. So why is it that it's an integer in that case? This was answered by Thouless and collaborators in 1982 for 2D electron gas, and Golterman, Janssen, and Kaplan in 1992. The two fields didn't know about each other's calculation for a long time, but the calculations are similar in spirit. What you can show in that case is that the Feynman diagram, corresponding Feynman diagram, which gives you the Chern-Simons level in that case, can be massaged in this following form, where this S are the Dirac operators on the lattice, at least for the lattice quantum field theory. This S is the Dirac operator, and it basically gives you a map from torus, so 3D torus, which is a momentum space, to a Dirac space, which is again a 3D space. And so this combination computes the winding number of that map. Okay, and so that's why it gives an integer. So the similar story for the generalized Hall current, the momentum space integral in the yes.
All of these people who didn't know about each other's calculations, they were all in the same department. Yeah.
Yes, that's the interesting thing. One thing, what I've heard is that Thouless was very quiet, and so yeah, that's what I. Yep. All right. Yeah, so the momentum space integral in the Feynman diagram, again, is computing a winding number of a map that's specified by some Dirac operator, even in this case. It's governed by the nth homotopy group in n dimensions. So it's a short version of the calculation. I'm not going to tell you in detail what's happening. So this is my K0, the full four-dimensional propagator. You can write in terms of D zeros. it's the same thing. I have taken my Dirac operator with index, or fermion operator with index, and I have expanded in this variable alpha, the angular variable. So D0 is a 2D fermion operator. You can use it to define a special unitary matrix like this. And this special unitary matrix is a map from a compact 2D momentum space to a 2D Dirac space. And so the Feynman diagram can be manipulated to rewrite as a winding number of this map. So the index in this case is a winding number in momentum space times the winding number in coordinate space. So this expression is, so this part of the expression is a winding number in coordinate space, and this 1 is a winding number in momentum space. So the Feynman diagram is computing, for the Majorana example, the winding number of a map from S2 to S2. The winding in the specific example of using the fermion operator is 1. So that explains the 1 in the Feynman diagram result. Note that when I turn on the gapping, which gapped out the two Majorana modes, it destroyed the index by setting the coordinate space winding to 0. So it set the winding of phi 1 and phi 2 to 0. The momentum space winding remained unaffected. So this is my conclusion slide. So we have constructed a Hall current analog for Majorana 0 modes living in 0 plus 1D dimensions. A similar construction works for all free fermion theories that we have looked at. With appropriate diagnostic fields, you have to turn on right diagnostic fields to create the 0 mode. So for example, you have 3 plus 1D topological insulator with 2 plus 1D massless edge states, 2 plus 1D chiral topological superconductors with these 1 plus 1D massless Majorana while and while fermion edge states. It works out for all of these examples, and there are several others that I haven't listed. Use one loop Feynman diagram to construct the current. The divergence of it produces the index, and the momentum space Feynman integral computes the winding number of a map from sphere to sphere. And so with that, I would like to end, and I would like to remind you, the hope is that we will be able to use this construction to tell the difference between gapped and gappable, gapped, but gapped and gappable gapless fermions in interacting theories. So that's the eventual goal, and thank you.
We've got plenty of time for more questions.
Some of the computation remind me some computation of the index under the, I think, tachyonic field using Kiren's super connection.
Okay.
And do you know whether there is some connection?
I don't know what that is. Yeah. The inspiration for this, the way we constructed the current, that comes from Kalaya's index theorem.
I see.
And some papers by Eric Weinberg in late 1970, where he was relating 0 modes inside a vortex with the winding number of the corresponding condensed field around the vortex. But he was looking at 0 energy solutions or time-independent solutions for the Hamiltonian. What we're trying to do here is sort of take the same idea, and we are looking at massless edge states for fermion operator. So yeah, that's where it's coming from. So our states are not time-independent states necessarily. They're just massless states.
What I vaguely remember the super connection computation is under the presence of gauge field and also scalar field like mass or tachyonic field. And when those tachyons are have diverging space-time dependence, and also gauge field has non-trivial instanton number, and in that kind of situation we can compute number of 0 modes.
Right.
Yeah.
Yeah, so here in this, hang on. this particular formula where I'm taking m to 0, I need certain conditions on my background field. I mean, in general, this index formula works for any m, provided your background fields fall off faster than 1 over r. But if that's not the case, as is the case with us, because we have these vortices, we need to take the limit of this m going to 0. So there are some constraints on the kind of background fields that would allow you to write this formula. Yeah.
This very naive question. Forget about the boundary. Just take 2D Dirac sheet. It's gapless. Can you detect that it's gapless by some such construction? I don't know.
Yeah. So as you can see, I need a description in this extra direction because my generalized Hall current comes from the fact that in my fermion operator I have taken both the bulk and the boundary. So the fact that I'm sensitive to the winding, for example, away from the,
goes in the
yeah. So
valve.
that's right. So if something is happening here, in order to detect it, I need to know what's happening here, and the information here is telling me what's happening. So yeah, given a description of the extra dimension, I can detect it. Yeah.
I mean, when you are constructing this setup with extra dimension, you have 2 domain walls, right? One, and you want to gap out only one. Would your construction see only one? I mean, your currents should vanish, but only for one side.
That's right.
Not for the other. How do you? I mean, do you just integrate the divergence over half the space, or?
That's what. So okay. You have to do it locally over half the space, because in truth, as soon as you have 2 domain walls, if I take the entire system together, index is immediately 0.
Yes, exactly.
So you have to compute the divergence of this current locally, because the total index is just going to be 0. So the hope is that you will see some local current here, and you won't see anything away. Yeah.
Thanks.
Yeah.
I sort of have a question for you and Acker, because this basic idea of taking discrete things and trying to embed them in U1.
Hang on, I could not hear what?
This idea of sort of extending to a higher dimension was introducing some new ones. So it sort of feels like there's some embedding of discrete anomalies into U1.
Yeah, so that is what I'm trying to clarify, that there shouldn't be, there isn't. Because if there was, if it was really an embedding, then I would not be hoping to distinguish between gapped and gappable fermions. And it's not an embedding. So you could say, for example, when I have 1 Majorana fermion, then I'm embedding it in a U1, right? So I have a Z2, I'm embedding in a U1 by doubling my U. But if you know, if you concentrate on the 2 Majorana fermion example, then there is no such embedding, because the U1 was there in my original theory itself, which is what I'm using to turn on the background field. So there is.
It's the same U1 as one condition.
No, it is the same U1. Right. So that's why there is the competition between the domain wall height and this master that I'm turning on, because both of them are being allowed in my original theory.
It's sort of twisted together.
That's right. So there is no embedding in the example where I've been interested in applying it. As soon as I have 2 Majorana fermions, I have a U1 that I can work with.
But then with the interesting 8 Majoranas, you've got an SO8, is that?
That's right.
playing some role?
So it's going to play an explicit role in the sense that if I look at this paper by Kitev, they have turned on a certain interaction which depends on the creation operators of these different Dirac fermions, C1, C2, C3, C4. And as soon as you turn it on, you get, you lose the ground state degeneracy on the boundary, which tells you that you don't have massless modes anymore. And we did that, we can compute this dUj mu. And note that I have now, I will define 4 U1s basically by combining 2 Majorana fermions from this 8. And I'm going to compute psi bar gamma mu psi, summing over all 4 of them. And the hope is that as soon as I turn on this particular interaction that they proposed with their SO8 symmetry in mind, as soon as I turn that on, I would just detect it. So it's, in that sense, it's very pedestrian. It's not some deep, there's no deep group theory going on here. It's just, the hope is that it's sensitive to the massless states that you have.
Any more questions? I've got a question.
Yeah.
So you mentioned in one of the earlier slides that there will be a generalized Hall current when you're dealing with finite groups, finite symmetry group. But here it seems that you enlarge the theories and you can compute always the current that you're using to get the index.
Do you think your question is different from what David asked? Because I do have, so I'm not enlarging, for example, in the 2 flavor case, right? When I write the Euclidean Dirac operator with a 0 mode.
Yeah.
So what I'm saying is that whenever you have this massless fermions in your original theory, there is a correspondence. I can write a corresponding Euclidean theory with 0 mode. And so there I may or may not enlarge the degrees of freedom depending on how many fermions I had in my original theory. So for the Majorana case, if I had 1 fermion, I do enlarge it to construct this operator with non-zero index. But if I have 2 Majorana fermions, I don't have to enlarge it. So I get a Euclidean operator with an index that's non-zero. Now given that correspondence that I have made, everything else after this construction of generalized Hall current, this is exact. There is no correspondence here. These are equal signs. Okay? So given an operator dE with a 0 mode, I can write this description of the same fermion operator, and I can describe it using a divergence of this current. So these are exact results. There's no correspondence. So I should have probably said that the given